Hello everyone, and welcome back to the second part of our tutorial on partial mechanism design and incomplete information industrial organization. My name is Kang, and I am an incoming postdoc at Harvard University. You might notice that this part of the tutorial is pre-recorded, and so I will not be able to stop for any live interruptions, but I should be in the virtual audience in case you have any questions during or after the tutorial. In the first part of the tutorial, Ellen introduced our motivation for studying partial mechanism design and described a unified framework for thinking about these problems. In this second part of the tutorial, I want to talk about applications of this framework before concluding with extensions and open questions. The first application that I want to talk about is on vertical contracting, which is inspired by joint work with Ellen. To motivate this application, we begin with the observation that many dominant firms do not necessarily sell a final good directly to consumers like you and me. Instead, these firms sell an input good to suppliers, who then use the input good to produce a final good. One example is Amazon, which sells distribution services to merchants, and then these merchants use these services to sell goods to downstream consumers. Another example is Google, which sells ad slots to third-party sellers, and then these third-party sellers use these ads to make the final sale. Now, there are many papers that study contracting, but relatively little is known about how the downstream market impacts upstream contracting in these vertical market structures. By examining this contracting problem, we can study when dominant firms should be allowed to merge with third-party sellers, that is, how vertical mergers impact welfare in the market, and we in fact do this in the paper. In this tutorial, however, we content ourselves with studying only the contracting part of this problem. Namely, we look at the question of how does the dominant firm optimally contract with third-party sellers. So here's an overview of our model. There is a dominant firm that sells an input good, which we model as a monopolist. This firm then supplies input to upstream sellers, or third-party sellers, who convert input into a homogeneous final good. Downstream consumers, like you and me, purchase this final good, and we summarize downstream demand by an aggregate demand curve. Let me now tell you about the specifics of the model and how they map from the unified framework that Ellen presented in the first part of this tutorial. There is a unit mass of risk-neutral sellers, each with unit input demand and quasi-linear utility over money. Sellers differ in types, which are denoted by theta, and theta captures the productivity of each seller. So each seller costlessly converts 1 unit of input into theta units of the final good. The game can be thought of as consisting of 2 periods, and so in the first period, sellers purchase input and convert it into the final good. And in the second period, sellers sell the final good in the downstream market at a price P. As before, we will analyze this as a single period game by summarizing each seller's payoff in the second period as his continuation payoff. Now, continuation payoffs depend on the downstream price P, the seller's productivity type theta, and whether the seller is allocated input. If the seller is not allocated input, then he cannot produce the final good for downstream consumers, and so he gets a continuation payoff of 0. If the seller is allocated input, then he can costlessly produce theta units of the final good. Since the price per unit of final good is P, he gets a continuation payoff of theta times P. Now, let me formalize the mechanism design problem. The dominant firm here acts as the mechanism designer and chooses a direct mechanism xt, which consists of an allocation function x and a payment function t. The allocation function x maps from each seller's productivity type theta to the probability x of theta that seller receives the input good. Also, the payment function t maps from each seller's productivity type theta to the expected payment t of theta that seller makes to the dominant firm. Given the downstream price P of the final good, the payoff of the dominant firm can be written as this formula over here. Crucially, key assumption A is satisfied, as we see that this formula over here is an affine functional of the allocation function x. This formula is very similar to the Myersonian revenue that a monopolist makes, but notice here that the dominant firm's payoff also depends multiplicatively on the downstream price P of the final good. Intuitively, the higher the downstream price P, the higher the revenues of third-party sellers, and so the more the dominant firm can extract through upstream contracts. Another observation that we can draw from this formula over here is that the extent to which the downstream market can affect upstream contracts depends on how variable the downstream price P can be, which in turn depends on the elasticity of downstream demand. In the special case where downstream demand is perfectly elastic, the demand curve is flat and only one price can prevail. In this case, our mechanism design problem reduces to a standard Myersonian problem, and so we would not need the tools of partial mechanism design. However, if downstream demand elasticity is finite, as we would expect in general, then this becomes a partial mechanism design problem, and the tools covered in this tutorial apply. To close our model, we need to describe the downstream market. Just as the price in the downstream market can affect upstream contracts, the price in the downstream market also depends on what upstream contracts the dominant firm chooses to write. In particular, the price P depends on the mechanism xt through this formula over here, but the total quantity, D of P, of the final good demanded is equal to some pre-existing quantity Q0 plus the quantity produced by third-party sellers. In turn, this depends on which sellers are allocated input. So a third-party seller of productivity type theta is allocated input with probability x of theta and produces theta units of the final good. Our previous observations on elasticity can be made formal through this formula here. With less than perfectly elastic demand for the final good, the demand curve D of P is downward sloping. And so the choice of allocation function x can affect the downstream price P in equilibrium. Intuitively, this captures the idea that more productive sellers, namely sellers with higher thetas, have higher willingness to pay for input, but they drive down the downstream price more because they produce more of the final good per unit input used. Finally, I also want to note here that key assumption B is also satisfied, as we can easily see that the right-hand side of this formula here is an affine functional of the allocation function x. Given the mapping from our unified framework into this application, our earlier characterization of optimal mechanisms must also hold in this setting. Namely, there exists an optimal mechanism that has a menu of at most 2 prices. This means that the upstream contracts that the dominant firm offers third-party sellers must be a simple menu that offers at most 2 options for how much input to purchase. One caveat here is that the direct effect and the indirect effect that we defined earlier is not useful for this particular application because of the multiplicative way that the dominant firm's payoff depends on the downstream price. Nevertheless, a very similar intuition applies. That is, rationing can be optimal here to trade off the total revenue in the downstream market and the total information rents made by upstream sellers, which in turn can be thought of as the cost of double marginalization. With further work, we can in fact say a little more about optimal mechanisms under regularity conditions, namely that rationing is not optimal if the ratio between the inverse hazard rate and theta is always decreasing in theta. This regularity condition can be thought of as the analog of the Myersonian regularity condition for this setting, and the exact form of the regularity condition itself is different over here because the equilibrium constraint does not take the form of a capacity constraint. However, I should also caution that this regularity condition takes a simple form because the model here in this application is relatively simple. This will no longer be true in the next application, which is more complex due to the richer economic environment that I'm trying to capture. This brings me to the second application, which is about redistribution with a public option in the presence of a private market, and this application is based on my job market paper. To motivate this application, I begin by observing that governments around the world often redistribute by providing public alternatives to goods sold in private markets, or so-called public options. Many of these public options are allocated at prices below market clearing levels. For example, public housing programs allow eligible individuals to rent affordable housing units at lower prices relative to private apartments of similar quality. Because public housing is offered at below market clearing prices, there is excess demand for public housing units, and in 2012, there were 1.6 million households in the United States on a public housing waitlist. But why do we ration public assistance to these households in need? One justification that policymakers often cite is that there are short-run constraints, such as limited funding and insufficient stock of public housing. Recent theoretical work has confirmed that rationing can be optimal when these constraints are present, and some of this work was also showcased in an EC tutorial last year. However, in this application, I want to put away these short-run constraints and imagine for a moment that we now have unlimited funding and can build as many public housing units as we want in the long run. The question then becomes, can rationing still be optimal in the long run? And if so, why? And so I will show that yes, in fact, rationing can still be optimal in the long run because of equilibrium constraints, namely public housing can potentially crowd out private apartments when both public housing and private apartments require a scarce input, such as the total amount of space available for housing. And so to this end, I will start out with a perfectly competitive private market, which takes in a scarce input, such as the total space available for housing, and produces private goods of different quality levels, such as private apartments of different sizes. Consumers have heterogeneous consumption preferences over quality. Now, this perfectly competitive market implicitly maximizes standard utilitarian objective. However, I will posit a policymaker with a redistributive motive who intervenes by providing a public option, such as public housing units. To capture her redistributive motive, the policymaker assigns heterogeneous weights on the welfare of each consumer in her objective function. The interesting case that I want to focus on is when the policymaker assigns higher welfare weights to consumers with, who consume lower quality goods. And so this captures the intuition that these consumers tend to be poorer than consumers who consume higher quality goods. The policymaker can screen individuals by exploiting this correlation between their consumption preferences and their welfare weights. This model is relatively more complicated because the public option here interacts with the private market through two channels, namely residual demand and residual supply. So on one hand, consumers who consume the public option no longer demand a private good, and hence the public option reduces the residual demand for private goods. Now, on the other hand, production of the public option also requires input. And so this means that the public option can potentially crowd out private goods by using up scarce input that could otherwise have been used to make private goods. And so the public option can also reduce the residual supply for private goods. Now, even though this model is more complicated, we can similarly map from our unified framework into this application, just as we did in the first application. There is now a unit mass of risk-neutral consumers, each with unit demand for a housing unit, be it a private apartment or a public housing unit. Consumers have quasi-linear utility over money and differ in consumption types theta, which determine their preferences over the size of housing unit they wish to live in. These preferences are described by utility function u of q and theta, where q represents the size of the housing unit. As before, the game can be thought of as consisting of two periods. In the first period, consumers apply for public housing, and after public housing allocations are realized, allocated consumers here will leave the market. The remaining consumers then proceed to the private market, which is what happens in period 2, where the competitive equilibrium is realized, at which there is an equilibrium price P, and this P represents the price per square foot of housing. Again, we will analyze this as a single period game by summarizing consumer payoffs in the second period as continuation payoffs. If the consumer is not allocated public housing, then he receives a continuation payoff given by his indirect utility from participating in the private market, where he solves his utility maximization problem of choosing the size of apartment Q to maximize the utility that he derives from that apartment, namely U of Q and theta, minus the price of that apartment, which is equal to P times Q. On the other hand, if the consumer is allocated public housing, then he simply receives a continuation payoff equal to U of Q public and theta, where Q public denotes the standardized size of a public housing unit. Let me now describe the mechanism design problem. So here there is a policymaker who designs public housing by choosing a direct mechanism XT by which to allocate public housing. In the paper, I allow the policymaker to also choose the standardized size Q public of a public housing unit, but in this tutorial, I consider a simpler version of the model where Q public is exogenously given. As in the first application, the allocation function X determines the probability X of theta that a consumer of consumption type theta receives public housing. And the payment function T determines the payment T of theta that consumer makes to the policymaker. Now, the payoff of the policymaker consists of three parts. The first part is the expected weighted consumer surplus, where the expected consumer surplus of a consumer with consumption type theta is weighted by a social welfare weight omega of theta. For example, consumers with lower theta might consume smaller private apartments, not because they value apartment size less, but rather because they are poorer and value money relatively more. And so a redistributive policymaker might assign a higher weight to these consumers. Now, the second part of the policymaker's payoff is the policymaker's revenue minus the cost of supplying public housing. Notice here that the higher the equilibrium price P, the higher the policymaker's cost. And finally, the third part is simply a function of the equilibrium price P, which might capture the surplus or weighted surplus of producers. As we can see, the payoff of the policymaker depends on the equilibrium price P through three different channels. So first, the policymaker cares about consumers who purchase in the private market and who are thus exposed to the equilibrium price. Second, the policymaker cares about her own costs of supplying public housing. And finally, the policymaker cares about producer surplus. In its current form, the payoff of the policymaker depends on both the allocation function and the payment function, but we can rewrite this as an affine functional of only the allocation function X by invoking the usual envelope theorem argument. And so the key assumption A of our unified framework is nonetheless satisfied here. Finally, let me describe the private market. The equilibrium price P in the private market depends on the mechanism through which the following equilibrium so it depends on the mechanism through the following equilibrium condition, which states that the total supply for the input good, that is space for housing, must be equal to total demand for the input good. Total supply is represented on the left-hand side by a supply curve S of P, and total demand on the right-hand side consists of the total amount of space used by public housing and the total amount of space used by private apartments at the price P. And so this captures the idea that space for housing is scarce. So for example, cities have limited space, and consequently, the supply of space is captured by an upward sloping supply curve S of P. In turn, this means that public housing units can potentially crowd out private apartments by using up space that could otherwise have been used for private apartments. And so this crowding out channel potentially drives up the price of space for housing. We also note here that key assumption B is satisfied in this formula, as the total demand for space on the right-hand side is an affine functional of the allocation function X. At the cost of some complexity, this model yields a rich economic environment that we can study. And so to illustrate the richness of this environment, let me just show you one of the implications of incentive compatibility in this setting. That is, for any incentive compatible mechanism, the probability of receiving the public option is quasi-concave in consumption type theta. This is a consequence of Meyerson's lemma, applied not to consumption types, but rather effective consumption types, which is equal to the difference between the utility that consumers derive from the public option and their indirect utility from consuming in the private market. In particular, one can show that the effective type function eta is quasi-concave in consumption type theta. And since Meyerson's lemma implies that allocation probability is increasing in effective type eta, and also remembering that increasing transformations of quasi-concave functions are also quasi-concave, hence allocation probability here must also be quasi-concave in theta. And so to visualize this result, suppose that we lined consumers up according to their consumption types. Initially, at the laissez-faire equilibrium where the policymaker does not intervene, every consumer purchases the private good, as you can see from this figure here. Now, this result implies that the first unit of public housing must be allocated with the highest probability to the consumer with the highest effective consumption type. And so in this example over here, that corresponds to this consumption type theta star. Subsequent units of public housing must then be allocated according to consumers' effective consumption types. And so all of these consumers in green here must be allocated with higher probability than consumers who are even further away from the consumption type theta star. And so intuitively, richer consumers, namely those with higher theta, have such a high value for quality that they are likely to proceed to the private market and get a private good of even higher quality than the public option. However, poorer consumers, namely those with lower theta, have such a low value for quality that they are also likely to proceed to the private market and get a private good, but of lower quality than the public option. As before, our characterization of optimal mechanisms must also hold in this setting. That is, there exists an optimal mechanism that is a menu of at most 2 prices. This result means that rationing can be optimal in the long run to trade off the direct effect and the indirect effect. I want to emphasize here that these are different from short-run justifications, such as capacity constraints and budget constraints, because it is long-run equilibrium constraints rather than these short-run justifications that lead to the optimality of rationing in this model. Recall that the direct effect here is equal to the difference in weighted social welfare due to the screening mechanism, which holds fixed the equilibrium price at P and measures the value due to screening. On the other hand, the indirect effect here is equal to the difference in weighted social welfare due to the change in equilibrium prices holding fixed the mechanism at no intervention. And so this measures the value due to pecuniary externalities. In what follows, I want to give you an intuition for when rationing is optimal. And so suppose again that we line consumers up according to their consumption types here. We start by considering the laissez-faire equilibrium at which the policymaker does not intervene. And so here, all consumers will consume private goods. Consumers who consume lower quality private goods, namely those towards the left of this axis, are poorer and have higher welfare rates. The supply curve for input is shown over here, and at the laissez-faire equilibrium, the total amount of input used is Q0, and the price per unit of input is P0. Now, this story revolves around this particular consumer over here, shown in the red dot, who is the poorest amongst all the consumers here. So let us suppose that the policymaker assigns a sufficiently high welfare rate to this consumer and wants to redistribute to this particular consumer. However, the policymaker cannot simply give this consumer the public option because of incentive constraints. And so if the policymaker does not ration the public option, then incentive constraints mean that the policymaker will have to allocate the public option with probability 1 to all of these consumers in the middle with intermediate consumption types first, namely the consumers shown here in green. And so in this example, doing so increases the total amount of input from Q0 to Q. And this will be the case when more consumers initially consume lower quality private goods rather than the rather than the public option. And so the public option induces these consumers to substitute their quality consumption upwards. You can see, however, that in this particular example, the supply curve for input is initially flat. And so increasing the total input from Q0 to Q does not change the input price by very much. However, if the policymaker here tries to expand the public option in order to redistribute to the poorest consumer without rationing, then the total amount of input use will continue to increase. And here, because there is a sudden steep increase in the input supply curve, the input price increases drastically. And this can lead to a large but negative indirect effect if the policymaker does not ration the public option. On the other hand, if the policymaker allocates to the same set of consumers with a slightly lower probability, represented here with a dashed green line instead of a solid green line, then there is a small reduction in the total amount of input used in the market, but this will lead to a large reduction in the price for input. In this example, rationing will therefore achieve roughly the same positive direct effect, but it will have a much smaller negative indirect effect relative to a mechanism without rationing. And so rationing the public option will perform better than not rationing the public option. Let me conclude this tutorial now with a discussion about extensions and takeaways. And so first, in the way of extensions, I want to emphasize that many assumptions that we made in this tutorial were for the sake of simplicity. Many of these assumptions can be relaxed. And so, for example, even though we assumed that agents have unit demand or unit supply in our framework, we can go beyond the unit demand or unit supply assumption by allowing for nonlinear utility functions. This is actually something we do in the paper version of the first application. In addition, even though we assumed in our framework that the objective function and constraints are affine in the allocation function x, these assumptions are not strictly necessary. The key idea here is that the partial mechanism design problem gives rise to a constrained optimization problem, and so we can nonetheless use other available tools to solve the constrained optimization problem, such as convex optimization and Lagrangian duality, rather than linear programming. Finally, I also want to draw attention to the fact here that the aftermarket does not need to be perfectly competitive in order for our approach to apply. And so, for example, in the second application, changing the market structure assumption to allow for imperfect competition is possible, and this would change only the number of constraints and the form of constraints rather than the approach itself. So what have we learned in this tutorial? Let me summarize our learnings with two key takeaways. The first takeaway is that equilibrium effects are important in many settings. Throughout this tutorial, we have seen that trade-offs in various economic problems can be understood via direct and indirect effects. For example, in the first application, we considered the problem of vertical contracting with a downstream market, where we allowed the dominant firm to choose the allocation of input. In this case, the price of the final good served as the indirect feedback effect due to equilibrium considerations. In the second application, we considered the problem of redistribution with the private market, where we allowed the policymaker to choose the allocation of the public option. In this case, the price of the input good served as the indirect feedback effect due to equilibrium considerations. Of course, there are many other economic environments that can be added to this table. And so here, I'm obliged to mention just one more, which is a paper of mine on the indirect regulation of externalities and will be presented at EC next month. Here, the problem is that a policymaker wishes to regulate externalities, such as pollution from cars. However, it is infeasible for the policymaker to measure pollution directly. And so here in this problem, instead of measuring pollution directly, the policymaker can tax some proxy good, such as vehicle mileage. In this case, the total amount of externality in the market acts as the indirect equilibrium feedback effect. As you can imagine, there are many open questions in the form of additional rows that can be added to this table simply by considering other problems, instruments, and indirect equilibrium feedback effects. For example, one can consider common market failures such as adverse selection, imperfect competition, costly search, and market frictions. One can also permute these with a variety of instruments such as taxes and subsidies on multiple goods, price controls, and product specification regulations. In each of these permutations, one can then think about what different equilibrium feedback effects might arise from using these different instruments. The second takeaway is that equilibrium effects can lead to rationing. Before this research program started, the common wisdom was that rationing arises from exogenous constraints, such as capacity and budget constraints, and also that rationing arises only for unusual distributions, meaning that standard problems typically don't require rationing. However, this tutorial has shown that equilibrium effects can necessitate optimal rationing, which means that rationing can instead arise for both natural distributions and also for endogenous reasons. And so, in summary, we have presented an approach for mechanism design problems with equilibrium effects in this tutorial. This approach has the advantage of using a lot of familiar tools from standard mechanism design problems and involves only slightly modifying these tools. Using this approach, we can study important equilibrium effects, which can lead to new insights on optimal mechanisms. Finally, there are many problems in partial mechanism design that are as yet untouched, and many potentially exciting and new areas for research, and we hope that this tutorial will inspire you to work on them. And so that brings me to the end of this tutorial. Thank you so much for coming to this tutorial, and I hope to see you in person at EC 2023.